Margaret, I have a two-part lecture on intermolecular forces. You told me you were doing that. I wanted to do it on the weekend, so I'm sorry I'm late about this. But here's a few slides. I hope they help you understand this material. So here I have just typed some sentences about phases of matter. So when we talk about phases of matter, it's a physically distinct, homogeneous part of a system. The properties of each phase are determined by the balance between potential and kinetic energy of the particles. Potential energy in the form of attractive forces tends to draw particles together. Kinetic energy associated with movement tends to disperse the particles. So you have this constant battle between the two, and who wins is going to basically let you know what phase you're in. So for an example, within a molecule, we want to be very precise that when we say intramolecular forces, those are the forces that keep a molecule together. So whether it's hydrogen gas or water, the intramolecular forces are the bonds. And you talked about bonds recently, a couple of chapters ago. The chemical behavior of each phase of matter is the same because the same basic particle is present in each case. What that means is, if you have some molecule A that loves to attack water, it doesn't matter if it's a solid, liquid, or gas. That's going to happen. And the reason is because chemistry is essentially focused on these intramolecular forces. This chapter is about intermolecular forces, the forces between molecules. So if I have a water molecule here, we're interested in what keeps that molecule stuck to another molecule. So let's say you have some snow outside, that's water in the solid form. We're concerned about this force that's attracting one water molecule to another. Now the way that I've drawn this, I've given you a little bit of information that it's actually the hydrogen on one water which is attracted to the oxygen on another. Now these are considered physical behaviors because each phase depends on these forces. So water and steam and ice have different physical phases based upon this, not the intramolecular forces. Intermolecular forces are abbreviated IM. They're the attractions and repulsions between molecules. They're not the chemical bonds like sigma and pi. That language is used for that. Intermolecular forces of a substance may exhibit are a function of the charge, if you have ions or if it's neutral, if it's polar or nonpolar, and how heavy the molecule is. So that's why this kind of has its own chapter. There's a lot going on here. There's a lot of different variables that contribute to intermolecular forces. So just a review again of phases. When you have gases, you have a lot of empty space between the molecules. So that makes them very easily to be compressed and also makes them very easy for them to flow. So you could have big weather systems like a tornado. Basically, that's all gas molecules. Liquids conform to the shape of the container, but the volume is limited by the amount you have, whereas gases fill the container and the volume is whatever the container is. You can't really compress a liquid, obviously, but it does flow pretty easily as long as you have pressure, let's say putting water through a hose. Solids maintain their own shape. They don't fit the container. You can't compress them hardly at all, and solids obviously really can't flow. So the kinetic molecular view of these three states. So this is kind of an outcome of the gas phase chapter. I still owe you that second part, but I can mention that later. So remember how we said in the beginning part of this lecture that you have attractive forces versus the motion, the kinetic energy? Here's what's going on here. When you have a gas, the attractive forces are so weak, the motion of the molecules overtakes them, and so therefore those molecules are just flying around in the air because they'd rather be by themselves than attached to each other. Particles are far apart, a gas has no fixed shape or volume. When you get to a liquid, what's going on is the attractive forces are stronger because the particles have less kinetic energy. So that's why they stick to each other, but they can flow because the attractions aren't so fixed. When you get to a solid phase, the attractions dominate the motion. The molecules really are fixed in place. They're not flying around, and that's why a solid has a fixed shape and Phase changes involve some vocabulary here, and I don't know why it did this, but if you look at this graph, you could see that you've got solid, liquid, and gas, and we have different words to transition between one another. So you know these from when you were, as long ago as when you were a kid. A solid goes to a liquid, you call that melting. A liquid goes to gas, you call that vaporization. When a gas goes to a liquid, you call that condensation. When a liquid goes to a solid, you call that freezing. Now, the two words you maybe don't remember or never knew is that when a solid goes straight to a gas, it's called sublimation. When a gas goes straight to a solid, it's called deposition. If you take a look, you've got some comments here about endothermic and exothermic. So basically what this part of the graph is saying is that in order to go from left to right, you basically are adding energy, so it's endothermic. If you're going from right to left, it's exothermic. You are giving off energy. You don't require energy. So two familiar phase changes, they have frost appearing on a window, that's deposition. Basically, you have water molecules that are in the air, in the gas phase. They're basically sticking to your window and they're forming ice, which is the solid phase. Vaporization involves, let's say, you getting sweaty and then the water molecules go up into the gas phase after they were in the liquid phase on your. So these bar graphs indicate the delta H of these different phase changes. Now take a look at the words here. The delta H of fusion is the enthalpy associated with going from a solid to a liquid. I always thought that was kind of weird because I think of fusion as something becoming harder, but in this case it actually is the process of solid going to liquid. So if you want to take, what's the units here? So this is kilojoules per mole. So if I have 1 mole of methane in the solid phase, basically they're saying it's going to cost you 0.94 kilojoules to make a mole of that melt. Melting basically is the same as this fusion process, solid to liquid. Notice, however, that if you want to do the vaporization, that's the liquid to the gas, it costs way more energy. It's going to be 9 kilojoules, 8.9 kilojoules per mole. Now we'll talk about in a minute why that is, but take a look that that's basically going on for all of these materials. The delta H of vaporization is always substantially more than the delta H of fusion. So this graph kind of shows why, using water as an example. See, if you're melting a solid to a liquid, you're just loosening the interactions between the water molecules so that they kind of flow. They're still considered a condensed phase. So the melting process, if you think about it being the length of this arrow, doesn't really cost you a tremendous amount of energy. On the other hand, if you go from the liquid phase to the gas phase, you have to completely separate every water molecule from every other water molecule. And that's going to cost a lot of energy because they're not touching anymore. And so notice that the length of this arrow, the vaporization arrow, is much longer than the melting arrow. Remember how I mentioned sublimation earlier? That's basically if you add up both of these red arrows. The words we used about going the other way are here. So condensation, going from a gas to a liquid, and then freezing, going from a liquid to a solid. Deposition is gas to a solid. Notice that these are just the negative values of the processes that were on the left. They're exothermic. Within a phase, heat flow is accompanied by a change in temperature. I think you learned this a few chapters ago, where Q is equal to an amount. It could be moles or grams, multiplied by a heat capacity, or you could think of it as a specific heat, put C, and then delta T is a difference in the temperature. Remember that as final minus reverse. Final minus initial. Whoops. I don't know what I mean by reverse. Final minus initial. During a phase change, heat flow occurs at a constant temperature, so you don't use that equation. You use Q is equal to the amount times the delta H of the phase change. So it might be vaporization, it might be fusion. You need to know which one you're dealing with. This is kind of an interesting graph because it shows you the process of taking, the way they decided to do this is you have 130 degrees Celsius steam. super hot steam. And they're by working from left to right, you're going to make this ice way down at minus 40 degrees. Now what this graph is showing you is that happens in 4 different processes. And you actually need to, sorry, 4, I mean 5 different processes. You need 5 different steps to calculate how much total heat is released. So they're doing this as cooling off. You could do the same thing the other way and call this a heating curve. The way that this book is done is decided to call it a cooling curve. So first you have to do this. You have to cool the steam. And that's when you're going to do something like an MC delta T type calculation. And you got to make that a negative because you're cooling off. A phase change, remember, this is the gas and liquid. This is going to be the negative of the heat of vaporization. Because the heat of vaporization is boiling something. This is the opposite. That's why all these negatives are cropping in. Now I have to cool the liquid. And again, I have MC delta T. Now be a little careful here. The specific heat of steam is different than that of liquid water, so you have to make sure you look that up correctly. Then we have the negative of the delta H of fusion times whatever the amount is. Usually this is kilojoules per mole. Whoops, I forgot to do that over there. And so you need to multiply that delta H by the amount. And then finally, you want to freeze. And freeze is going to be another negative MC delta T, but the C again is different because now you've got the specific heat of ice instead of water. I hope that made sense. The scenes below represent the phase change of water. Select data from the previous text discussion to find the heat released or absorbed when 24.3 grams of water undergoes this change. So here we have a liquid going to a gas. Notice that you started at 85 degrees Celsius and ending up at 117. So basically you've got a variety of things to do here because they're talking about water. You've got 3 steps in order to solve this problem. You have to heat the water from 85 to 100 because that's the boiling point. Then you need to boil the water. For that you need the delta H of vaporization, and then you have to heat the steam. You have to go from 100 to 117. So there's a lot of work in this problem. And that's what they do right here. One of the things they do is they take the 24.3 grams and they convert it to moles because the specific heat that they gave you is in joules per mole. And so if you know the moles times the joules per mole and the delta T, you can get the kilojoules for stage 1. Stage 1 was heating up the liquid. Stage 2 was doing the delta H of vaporization times the number of moles, and stage 3 was heating up the vapor. So you have 3 different terms that all add up to an answer here of 57.2 kilojoules. Now, in a closed flask, the system reaches a state of dynamic equilibrium where molecules are leaving and entering the liquid at the same rate. So look what they've got here. They took a liquid, it looks like maybe tea or something colored brown or coffee, and they closed off the top. What they're telling you here is that if you just wait a little bit, we wait over time, even if you vacuumed out all the air and you waited a little bit, you would find that some of the liquid molecules are in the gas phase. That's just natural. It's called a dynamic equilibrium. Some of the molecules are vaporizing and some of the molecules are condensing. So the pressure of the gas form of this liquid is called the vapor pressure. Okay. What if you have like a volatile liquid, like let's say nail polish remover? Then you have a high vapor pressure. What if you have something like liquid mercury, which doesn't vaporize much at all? You have a low vapor pressure. So basically what we've got going on here is that this is sort of a version of the previous slide where you took the flask and you vacuumed out the air layer, but then you watched the pressure of the vaporizing molecules is going to eventually increase until it flattens out. That's what we mean by the vapor pressure. It's the pressure inside the flask exerted by the gas phase molecules that evaporated. Now, this is what's the effective temperature on the distribution of molecular speeds. We kind of jumped ahead a little bit in a way, but if you think again about the flask where you have a liquid and then some molecules that have vaporized, what we're saying is that the characteristics of these molecules in the vapor phase are going to change if you change the temperature. Now, the thing you might remember from the gas phase chapter is that when I have a temperature, let's say T1, of a gas, they're not all moving at the same temperature. Most of them are moving at this middle temperature, and some are faster and some are slower, but the bulk of them are in this middle part. On average, if you increase the temperature, the average molecule speed is going to increase. It doesn't mean every molecule will increase, it just means the average speed increases. So the thing you should notice here is the area under the blue curve is the same as the area under the orange curve, but the orange curve is more spread out to the right, where you have a lot more fast molecules. As the temperature increases, the fraction of molecules with enough energy to enter the vapor phase increases and the vapor pressure increases. So what that graph didn't show you, and maybe I should go back, I won't, I can't. What that graph didn't show you is that when I go to the higher temperature, T2, more molecules can evaporate. Okay? So that, again, as the temperature increases, the fraction of molecules with enough energy, that's the fraction beyond some arbitrary line, the vapor phase increases and the vapor pressure increases. If you have weak intermolecular forces, the more easily particles enter the vapor phase and the higher the vapor pressure. So that's kind of what I said earlier. The molecules can break free from the liquid either by being very volatile, they have weak intermolecular forces, or you could increase the temperature. This is an important graph because it shows you that different kinds of liquids have different vapor pressures profiles. So this red arrow is basically room temperature. What this is telling you is that at room temperature, water has a very low vapor pressure. Water evaporates very slowly. Ethanol, alcohol, evaporates much more quickly. Look, the vapor pressure is about twice as high. Ether has a very, very high vapor pressure. This is highly volatile. If you spilled some ether on the ground, even though it's room temperature, it would evaporate super quickly. Vapor pressure increases as the temperature increases. We said why that is on the earlier slide. If you cool off something, it's going to decrease the vapor pressure. Vapor pressure decreases also as the strength of the intermolecular forces increases. So what this is implying to you is that water molecules attract each other more than ether. Ether molecules have very weak intermolecular forces. What's special about this line? We'll take a look at 760. 760 is atmospheric pressure. Notice what happens. When the vapor pressure, of water reaches 760, notice that it happens at 100 degrees Celsius. That's what the boiling point is. The boiling point is the temperature when molecules want to break free. Basically, if you heat up water to 100 degrees Celsius, they have so much kinetic energy that they break free from any intermolecular force. The Clausius-Clapeyron equation, it connects vapor pressure to temperature, and so that's what they do here. If you know what the delta H of vaporization is, R is the gas constant, you can end up figuring out, you can end up getting it, rewind. If I took the vapor pressure, so basically that's P, and I plotted it versus 1 over T, I would get a straight line, and the slope of that line is negative the delta H of vaporization. So that's how chemists figure out what the delta H of vaporization is. They basically try to find the vapor pressure at different temperatures and make this plot. A 2-point form is used when the vapor pressure at 2 different temperatures are known. So let's say, for example, you knew the vapor pressure at one temperature and you wanted to know the vapor pressure at another temperature. You could plug those two numbers in. As long as you know delta H, you could solve for P2. You should practice this. I just graded my third exam, and the students made many algebra errors. Practice this equation. If the unknown is in the t, or if the unknown is over here, you have to know how to solve for it, and you don't want to make a mistake on your exam. This is basically what I already showed you. These linear plots are going to be the result of doing the natural log of vapor pressure versus 1 over t. Oops, sorry, it wasn't p versus before. It was natural log of p versus 1 over t. My bad. So here's an example. I give you some data. You could figure it out and compare your answer. Notice what I said before. The boiling point of a liquid is the temperature at which the vapor pressure equals whatever the external pressure is. The normal boiling point of something is when it's the temperature at which the atmospheric pressure is 760. As the external pressure on a liquid increases, the boiling point increases. So basically, gases, if it's higher pressure, you have more temperature needed to boil it. If you're up in the mountains and there's lower pressure, you don't need as much temperature to boil water. This is an example of sublimation, kind of interesting. So here you take iodine, which might be sort of impure, and basically you put a test tube inside a bigger test tube with ice in it. As the vapor evaporates, it crystallizes when it hits the tube. And so this is an example of pure iodine. So this is a purification method of some chemical. This is what's called a phase diagram. It shows you, if you know the pressure and the temperature of that system, then you know what phase you're in, solid, liquid, or gas. This is the phase diagram for CO2. The thing that's really weird about it is that at 1 atmosphere, which is normal pressure, if you have solid CO2 and you warm it up, it goes straight to the gas phase. It doesn't go to the liquid phase. The words we used earlier, melting and freezing, vaporization and condensation, those are words that are used when you cross from one phase to another. I'm not sure your teacher is going to teach you about critical point, but if you do, you should read the textbook to find out what that is. I'm getting a little tired and I have to go to dinner. Finally, notice how water is different. At 1 atmosphere, you do go from solid to liquid to gas as you raise the temperature. This kind of odd thing happens, though. The line separating solid and liquid is tilted backwards. What this means is you could actually have ice and add pressure and turn it into water. Kind of weird. All right, I hope this was helpful, and I get some more to you in the next couple days. Bye.